Hi everyone, my name is Kwan Nguyen. I'm a power system engineer at the Pacific Northwest National Laboratory. Today I'm going to present my work on the control and simulation of a grid forming inverter for hybrid PV battery plants in a power system BlackStart. This is the work where PNNL collaborates with the University of North Carolina as well as New York Power Authority. About the background of this project, as you might know, a black start process is a process of restoring power system following a major collapse or a system-wide blackout. This process relies on several units, which are called black start units. These units are not only able to start by themselves, but they also able to energize transmission lines and pick up loads. Recently, PV power plant can be considered as valuable black start unit because they have fast ramping rates, they have power ratings of several hundreds of megawatts, and also they are able to coordinate with energy storage to increase the reliability. So in this work, we developed the model and grid forming control for hybrid PV energy storage power plant as a reliable black start resource. First, we review the current practice of a black start process. Second, we develop grid forming capability for the plant inverter. Third, we develop PV and energy storage coordination at the DC side to supply power to the AC side. Finally, we demonstrate the control and the black start process using electromagnetic transient tuned PSCAS and IEEE NIBUS system. So this is a grid forming control scheme that we developed for the plant inverter. It has a primary control loop and secondary control loops. The primary control loop includes the droop curve and the familiar voltage and frequency control loop, voltage and current control loops. And for the secondary control, it has PI controllers here to make sure that the voltage magnitude and the frequency at the point of common coupling are equal to the set points. And here are the model of energy storage and PV. For the energy storage, we have to use a buck boost converter for the bidirectional power flow. For PV, we only need to use boost converter to boost the voltage here to a higher voltage here and apply this voltage to the inverter. For the inverter, we were able to test both the switching model and average model. And then we applied this grid forming control to this black start unit in an IEEE NIBUS system. And this unit is used to energize transformer and transmission lines and also pick up loads. The energizing sequence and how much power, how much load are being picked up at each step are given from an optimization solution. And the steps are shown in the circles here. During this process, we found out that if we energize a transmission line and or unload the transformer, there will be inrush current. And we solved this issue by adding auxiliary load at the secondary side of the transformer and transmission lines. This slide shows the results of the simulations. Here we have the voltage at bus 1 and bus 5. Here we have the frequency measure at bus 1. Note that bus 1 is where the PV power plant is located. And here we have the power supply by the entire PV energy storage plant. And here we have the breakdown of power supplied by PV and by the energy storage. So during the entire simulation, you can see that the frequency and voltage magnitude are stable. There are some fluctuations following each switching event, but it become stable quickly after that. Also, uh, uh, we can see that the simulation results in PSCAD closely match with the numerical solution from optimization solutions. Finally, the simulation time when we use the average model of inverter is much faster, much less compared to the simulation time when we use the detailed switching inverter model. However, only by using the detailed switching inverter model, we are able to observe the inrush current behavior. In conclusion, in this work, we developed grid forming control for inverters with primary and secondary control loops. The control is applicable for both switching model and average model of inverter. We were able to demonstrate the voltage and frequency stability during the entire backbone energizing process using an IEEE neighbor system. We were able to find a solution to handle the transformer and line energizing in rush current issues. And we believe that the grid forming model that we developed in this work can be used to verify the feasibility and numerical analytical results, for example, from a power flow or optimal power flow studies. Future work includes developing power sharing among PV among the PV energy storage power plant and other non-BlackStart units. And also we plan to migrate this grid forming model in PSK to a real-time simulation tool in operative hypersim for large-scale demonstration using NIPA system. Thank you.